In this video I shall present Cantor's proof of the fact that the cardinality of a set is always smaller than the cardinality of its power set. Fix a situation let x and y be sets and denote by p of x the power set of x, which is the set of all subsets of x. Recall the following definitions: that f from x to y a mapping, then f is called injective if different elements of x are mapped to different elements of y, if for a b in x with a different from b, one has f of a different from f of b. F is called surjective if every element of y is image of an element of x. If for every y in y there exists some x in x such that y is equal to f of x. F is called bijective if it is both injective and surjective. Most of you know well these notations. A new notation, or not so common notation, we use this symbol for a mapping x which sends x to a mapping which sends x to f of x. This is the same thing, a graphical variant of the expression lambda x f of x in lambda calculus, which is known in computer science and in logic. In LaTeX you may define new command fun matop big circ limits, and write then, for example, fun x of x square. Sorry, of course in LaTeX you have to write x sub, for example. Definition: if there exists a bijective mapping f from x to y, we say that x and y have the same cardinality, and write otherwise means that there does not exist such a bijective mapping. Otherwise we write x different from y. If there exists an injective mapping f from x to y, then we say that that the cardinality of x is less than or equal the cardinality of y, and write x less than or equal y. If in this case the cardinalities are not equal, we write now. Of course, one wants that it should be possible that the usual relations of such an expression remain valid, and this is in fact shown in set theory. These notations, concepts, and notations behave well. We will now show, this is the main part of this short video, we will now show that always x has a cardinality which is strictly smaller than the cardinality of its power set. This has already been shown by Georg Cantor. The principal inventor of set theory. His proof is mainly contained in the next lemma. Proof is short but ingenious. First remark: the mapping which sends x to the set consisting of x alone goes from x to the power set is clearly injective. Therefore, x is less than or equal to the cardinality of its power set. Now, the fundamental lemma there is no surjective mapping from x to the power set. We shall repeat it later, but soon, but it is clear that here follows there is in particular no bijective mapping between the two, and therefore we have shown what we wanted to show. Proof. Short but ingenious. Assume that this is not true. Let f from x bx be a surjective we want, of course, show that this leads to a contradiction, and define B as the set of all x in X such that X does not belong to f of x. We call f of x is a subset of x because the mapping goes from x to the power set. This is a well-defined subset of x. Since f is surjective, i.e. B is in P of x. Since f is surjective, there exists x in X such that B is f of x. Think about it for some seconds. B is a subset of X and the mapping reaches every subset. There are two possibilities. Exactly two possibilities. X in B or X not in B. Both lead to a contradiction for assume the first possibility. Assume X in B. Then, or better, but B is equal to f of x. Hence, x is in f of x. But this means x not in B. And we have here a contradiction. Other possibility, assume x not in B. This means, again, B is f of x, means x does not belong to f of x. i.e. x in B. Contradiction. With this, the lemma is already shown. A remark of literary nature. Proof is finished. Proof finished. Of the lemma is finished. This is an outside external remark. Reasoning as x in B or x not in B is very strong. It's a very strong idea of reasoning, which may lead to very far-reaching consequences. As the following famous quote by Arthur C. Clarke, well-known science fiction writer, which wrote, two possibilities exist. Is often quoted. Permit me to quote it also myself, two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying. Unfortunately, I cannot find the place where he wrote this. Maybe he wrote it in some of his philosophical papers, but I found it in a book of him, maybe in Rendezvous with Ram, but I am not sure. Compare with place with Krone in the references at the end of the lecture. Clark was a rather technical science fiction writer. He studied mathematics and physics at King's College in London and obtained a first-class degree, which I think is a higher bachelor degree. So, now we may conclude our theorem. The cardinality of x is smaller than the strictly smaller than the cardinality of p of x. Proof. This is now immediate from the results by the remark we have x less than or equal p of x, and by the lemma there exists no surjective mapping between the two, and therefore also no bijection. We have x different from p of x, hence x smaller than p of x. This is the main part of this lecture. I conclude with, for a little more completeness, with some well-known facts characterizing injective and surjective mappings. We did not use these in the proof of the theorem. First notation, id x denotes the identity, therefore the mapping xx from x to x, and similarly is defined the identity on y. Now some easy propositions. Assume that x is different from the void set. Then a mapping f from x to y is injective if and only if it has a left inverse, i.e. if and only if there exists a g from y to x such that g composed f is id x. Proof. Let f be injective and denote by im f the image of f. Since f is injective, for every y in IMF there exists a unique, well-defined element x in x such that f of x is y. We write then x g1 of y. This gives a well-defined mapping g1 from the image to x. Now, our mapping G should be defined on all of y, not only on the image. Here we use the hypothesis that x is not void. We can therefore, since it is not void, choose an element x0 in x arbitrarily and define g from y to x by g of y equal g1 of y if y in IMF and x0 otherwise. By definition, one has then g of f of x equal x for every x in x, and this means G composed f is identity on x. The converse is immediate. Let G composed f equal it x for some g, and assume f of a equal f of b. Then a is equal g of f of a, but f of a is also f of b, and this is b. Second proposition. A mapping f from x to y is surjective if and only if it has a right inverse. I.e., if and only if there exists g from y to x such that fg is equal identity on y. This requires the axiom of choice, as we shall now see, or is also equivalent to it. Proof. Let f be surjective. Then, for every y in y, there exists xy in x such that f of xy is y. By the axiom of choice, the expression denotes a well-defined set, which is the graph of our G. Intuitively, G is the mapping which sends y to xy. Problem is here that this expression looks as if it described a set, but it does not follow from the other axioms of a set theory that it is a set, that it denotes a set. By the axioms of choice, this is a set, and therefore it can be used as the graph of our G. Side remark, in proposition 1, we did not need the axiom of choice, since we had no choice. The element x being uniquely determined by the condition f of x equal y and by the injectivity. Okay. Second direction is also this time easy. The converse is immediate. Let f compose G equal e to y. Then for every y in y, we have y equal f of G of y, and this means y is in the image of f. Concluding proposition 3. Let x different from void. Then the following statements are equivalent. There exists an injective mapping f from x to y. Second, x has cardinality less than or equal that of y. There exists a surjective mapping G from y to x. Proof. Now, 1 and 2 are equivalent by definition. 1 implies 3. Let f from x to y be injective. Since x is different from void, by proposition 1, there exists G from y to x such that G composed f is identity on x. But then G is surjective by proposition 2. And 3 implies 1 is the same. Let G from y to x be surjective. By proposition 2, there exists f from x to y such that gf is equal to x by proposition 1, f is injective. This is everything. I would also indicate some references. Czysielski, set theory for the working mathematician, in German Oliver Deiser, Einführung in die Mengenlehre, Springer 2004. For the action of choice is Springer lecture notes by Horst Herrlich. Action of choice. Springer lecture notes, mathematics, appeared 2006. And at a very high level, Thomas Jech, set theory. Springer 2006. And then about the philosophical writings of Arthur C. Clarke, Arthur C. Clarke's philosophy for the 21st century, which appeared in the Journal of Space Philosophy. So this is the 8th of June 2021. I am Josef Eschkfeller. Thank you very much.